Okay, here we are on the 5th day of February. I'm counting down my days because my deadline with my editors is going to go by fast, and I'm continuing to work beyond craziness, but this is all part of the fun. I'm handing your quizzes around right now. I'm going to put together a histogram. Hopefully between now and Thursday I will take out some time and actually post a histogram on the website. I'll post the key that I've got displayed right here on the website. And we'll be gearing up by the end of class today for a second quiz. I mean, I could hold off a week, but the way I look at it right now is I'll just keep the pressure on, because that way you'll keep, working hard. And if we do enough quizzes, I'll drop 2 quizzes then. I mean, practice makes perfect, right? So I think it will work. It just is the time taken out of lecture to do it. I'm really not, unless you want to have me go through this quiz, I'm ready to jump back over into Fourier analysis. But if anybody wants to ask a question right now on the quiz, or just simmer on it and bring it up on Thursday, I wanted you to get them back so that you could see the style. I do have a grader. She's a PhD student. She actually graduated from our program, and I think her master's is in math, if I'm thinking right. I could tell you a bunch more things, but I know you wouldn't be able to guess who it is, because it's somebody that keeps an extremely low profile. So any comments, or ready to go into Fourier transforms? Pardon me?
I like her grading. It's very nice.
Right, nice and neat?
Yeah, she explains things.
Well, let me tell you how nice it is that she did for you. I mean, I've got the hours to spend. Not only did she do that, she has this nice key that tells exactly how she fractionalized all the points.
Oh, wow.
And made comments on things. So
Give her a raise.
I think I'm paying her all I can pay a grader right now. But I do have extra cash to pay in case she runs up too much. I mean, I don't know if you guys know this. Some of you probably grade, right? Any of you ever grade? Okay. Well, one of the things about being a grader is you're told to only spend so many hours grading papers. So I've had graders before that have been getting bonked because they're turning in too many hours, and then the quality of the grading is really subpar. And I say, you can't do that, because the students aren't, this is on homeworks typically, they're not learning anything. So I say, you got to work harder, you got to be more detailed, because this is not working. But everything costs money, and I guess that's what it comes down to. Higher ed isn't cheap, and if you want to do a quality job, time is money. So it's just the way it is. If your parents are supporting your higher education, that's what you got to tell them. Engineering school is expensive. Okay, I'm going to go over into Chapter 2, and then we'll bounce back into the other homework problems. I also posted a second homework sheet up there, so there's a set number 2 posted that's leads off with some Fourier analysis. It leads off with, as a matter of fact, a PN sequence generator, which is one of the things you're going to be doing in the lab. Those of you in the lab, you're going to use a microcontroller to generate a pseudorandom code and analyze the spectrum of that. So there's a homework problem that goes through that analysis. So where we left off, we were looking at some theorems for Fourier transforms. We had just looked at the delay theorem before the quiz started. And the next theorem up is the frequency translation theorem. And I drew these green arrows on here because I was just saying, kind of at the closing, I believe that from the duality theorem, which is going to be coming up on the next page, frequency translation is the dual of the time delay theorem. And since it's up on this page still, do you notice that similarity? We're doing a time shift on the time domain side, and we're doing a multiplication by complex exponential on the frequency side, and then the dual of that is, if we do a shift in frequency, we are multiplying by complex exponential on the time domain side. That's duality, and we'll use that for some other business a little bit later, but just homing in on the frequency translation theorem. This is one of the more important theorems in communications theory. You know, if I was to rank them, this would be like a star, and this one down below here, which is related to it, would be like a double star. Used an awful lot in chapter 3 when we get into actual modulation theory. So frequency translation says if we multiply a signal by a complex sinusoid, e to the j 2 pi f naught t, so what's the polarity on that complex sinusoid frequency-wise? Positive or negative? It's positive, right? So the way I think of it as we have a signal x of t, and that complex sinusoid is, if we envision what it does in the complex plane, this point is sitting out here spinning around counterclockwise in the complex plane at some rate, and that rate is f naught revolutions per second. Does that make sense?
Yeah.
So our signal x of t is getting multiplied by that, and a crude way of visualizing that is the signal is getting spun around and around by the complex sinusoid. We're spinning it, and we're spinning it with a positive frequency, so I call it spinning it up in frequency, like that, so it's going up in frequency. And the Fourier theorem says that the spectrum of the signal onshifted, which is x of f, moves up to being centered on f naught. I'm trying to give you something to help you memorize this thing by. So a positive frequency shift is what the minus sign here does. The spectrum goes from being at, the spectrum is at 0. When we shift it up in frequency, it moves up here to be at f naught. So if the sinusoid complex sinusoid has a negative frequency, then the signal is being spun down in frequency, and we'll shift it negative. But it doesn't mean that we have to start with the signal at 0. We could start with the signal at a positive frequency and then spin it down to 0. So there's all different, applications of the frequency translation theorem. The proof of it is exceedingly easy because you just plug the signal in to the Fourier transform integral, and then you move that complex exponential in with the complex exponential of the Fourier transform itself. And when you do that, you've got this argument f minus f naught sitting in place of f, and you stand back from that integral and you say, it looks like the Fourier transform just of x of t all by itself, except now I have a new variable. Instead of having f, it's f minus f naught. And what could be simpler in terms of a proof? This is one of the easiest proofs there is in Fourier theory. So it shifts it up in frequency. Now, what's the downside of this operation? Does anybody see something that's not too cool about this theorem? Suppose x of t is the output of a function generator, like the BNC port, so you've got it coming out on a cable. And what do I have to do to multiply it by a complex sinusoid? What do I actually have to do physically to implement that? To generate actually two signals, right? Because this e to the j 2 pi f naught t is complex. So I actually have to generate a cosine 2 pi f naught t plus a j sine 2 pi f naught t. And that's pretty awkward to do in the lab in the natural setting. But we'll see how things like that can be manipulated by other means. There's actually microwave components, it's called a quadrature hybrid, that you can input a cosine into a microwave circuit called the quadrature hybrid, and it will output a cosine on one port and a perfectly quadrature or 90-degree phase shifted sine comes out the other port. That doesn't take care of the J part of it, though. The J is still something to be reckoned with. Well, you have to have two signal paths is what you have to have. You have to basically have two physical paths in the electronics to make this work. So that's not good. However, in digital signal processing, it's not a problem. So if you're doing this in the discrete time domain, which you learned about in 2610 and 3205, for example, this would just be keeping, a real and imaginary part in an array somewhere or in memory. So then it's not a problem.
So to digitize it, sampling like that,
With an A to D.
it's within MATLAB type coding structure.
You can do it in MATLAB, yeah, beautifully.
It's not an actual circuit. It's a simulation of it.
No, you could do it in real-time digital signal processing too, where you have the other class I teach after this is real-time DSP, and we have a processor. You might do it in FPGA, something like that. But you can actually do it in hardware too. It's just that you're going to have a complex signal, so you have to have two signal paths to do that. Now the modulation theorem doesn't require this, but it has a downside. Modulation theorem is what we refer to most frequently, and the modulation theorem is a variation on frequency translation. Modulation says you multiply signal times a cosine 2 pi f naught t, and what that does is that moves a copy of the spectrum up to f naught and down to minus f naught, and then there's a factor of 1/2 because of Euler's identity for cosine. In other words, when you look at the proof, you see where that 1/2 comes from. To do the proof, you just take the cosine that's sitting over here, and you break it apart into two complex sinusoids from Euler's identity, and then you go through and apply it term by term, so that this piece right here is getting multiplied times x of t, and then this piece here is getting multiplied times x of t. So from the frequency translation theorem, you've got a 1/2 and a positive complex sinusoid, so that's spinning it up in frequency, and then you have the e to the minus j 2 pi f naught, which is spinning it down in frequency or shifting it down. The beauty of this, though, is it is real, because if x of t is real and cosine, of course, is real, the signal is real, and it's shifted. Later on, when we get into chapter 3, we'll use this very frequently. As a matter of fact, this is kind of the block diagram of a simple modulator or multiplier. I'm calling this a modulator because it'll be a form of amplitude modulation and double sideband modulation in chapter 3. Right now it's just simply a block diagram to represent the operation of the modulation theorem. So if x of t has a spectrum that's centered here, and suppose that's bandwidth w minus w, then the modulation theorem, when you multiply by the cosine in your ideal multiplier in this figure, it shifts a copy of it up and a copy down. So the good thing is it's a real signal. The bad thing is we have two copies and maybe we only wanted one. So we'll also be exploring something called the Hilbert transform a little bit later on. The Hilbert transform can do something with a certain type of filter, the Hilbert transforming filter, and do this in the as a real signal and still maintain the only one copy. But it's more complicated to implement that way. That'll be your first computer simulation project. We'll be building a single sideband modulator out of filters and multipliers in MATLAB. The other thing that you'll do in the comm lab, though, is you'll look at this multiplier, and on paper this looks really simple. This is the schematic for the multiplier, just a circle with an X through it. You know, just like you have a circle with a plus sign is a summer. The summing is not too bad in electronics. The multiplication is pretty tricky to do in analog electronics to get it done properly. So in the lab you'll be looking at some double balanced mixers, which is a microwave or RF circuits term for a multiplier, and they're far from perfect. They produce a bunch of other spurious components. But on paper, like right now, if that's the symbol, that's the ideal multiplier. It's just a bit of a dream in analog. Any questions? Okay, here's just the statement of the duality theorem. And what it says is you can put something in the time domain side that looks like a frequency spectra, and what comes out on the frequency domain side is then like a signal, a spectrum that's been Fourier transformed a second time. It comes back to the time domain, but because of the sign changing that goes on with the plus and minus complex exponential in the Fourier integral, it comes back flipped over as x of minus f. But in many applications of the duality theorem, that this inversion doesn't matter if the spectrum is, or the signal is even. So if it's an even signal, then that minus sign doesn't mean anything because it sort of goes away. This example right here is to try to demonstrate that and also develop another very important transform pair that we use in modeling. This transform pair is trying to establish what is the time domain signal corresponding to a band-limited or rectangular spectrum. And we know from last week that when you Fourier transform the pi or rect function, remember I said this would be easy to memorize? Does anybody have it memorized? Okay, what is it?
It is 1 for t is less than tau.
No, that's one.
No, what is the Fourier transform? Does anybody have that memorized yet? I don't have an a in here, but I could throw one in. So it's a tau times what? F. Not Fn, because it's not a Fourier series, but it's a Fourier transform. Just F tau. Too amazing, or I'm just smiling because I'm just trying to see where you're at, trying to remember some things. You will have, on your first exam, you will be allowed to have a crib sheet of Fourier transform pairs and Fourier series properties and whatever else you need. But
Do we have to create that, or will that be provided to us?
I have to decide. Do you want me to create it for you? I mean, what you can do, or I suppose what I might do is just copy what's in the back of the book in the appendix, and then I'll just hand it out. But where are these great things? Well, on page 724, you've got the transform pairs, and then you've got the theorems on the other side. So to work with duality now, what is the time domain side of a rectangle in frequency? Our immediate hunch would be that if a rectangle in time is a sink in frequency, a rectangle in frequency should be a sink in time, right? Because of the duality property. So if you can plug into duality specifically, and this is, plugging into the duality theorem is kind of mind-boggling in a way, because you go back to the theorem and you say, okay, it says, says on the left side I plug in the spectrum but put t in place of f, and what comes out on the right side is the Fourier transform of that big X in the forward direction, but with t replaced by minus f. So in this case I plug in to the rect function in frequency, but I plug in t in place of that. And then I say, from what I wrote at the top of the page here, that in the frequency domain that would be the pulse width, which is 2w times the sinc of the pulse width times f, and that is equal to little x of minus f. But then to back out of this whole deal, I eventually have to get time back in there, so I have to swap the rules back again just to make it go to officially be in the time domain. So in this case, because sinc is an even function, the minus f versus f doesn't matter because it's even. And then I replace f by t, and then I've got what I have in the blue box, namely that 2w sinc 2wt is equal to pi f over 2w. Why the 2 when the pulse was just tau? Well, in the frequency domain side, we like to think of the spectrum of a signal that's runs from 0 to some frequency as being what's called a low-pass type spectrum. Low-pass meaning it's centered at 0, it occupies a band of frequencies up to some positive w, and then goes away. So this represents the bandwidth. The bandwidth is not measured in this case as the two-sided bandwidth because it's a low-pass spectrum, as it's called. So it's from 0 to w. So that's why he's got it set up that way in the book. Whereas on the time domain version of this, you want it as tau because you're interested in the full pulse width of tau. But everything tracks. I mean, tau gets replaced by 2w and so on. Okay, so we got that done. Now here's a little theorem that can be helpful, and I'm going to use it to get at something without having to do something more directly. But first we have to get the theorem established. This is the differentiation theorem, which is not totally trivial to prove, but the result is fairly easy to remember. You differentiate a signal n times, and that takes its spectrum of the undifferentiated signal x of f, and you multiply it by j2 pi f to the nth power. To not take it to such an extreme right away, suppose it's just n is equal to 1, just one derivative. So one derivative you can get at with integration by parts, which I'm not particularly fond of anymore. I wasn't fond of it a whole lot in calculus, although I lived through it, and I've used it in other proofs elsewhere, but it brings back memories of a particular college roommate I had that made up a little song about that. He made up a song to memorize this formula for integration by parts. It's not something I'd repeat in public, but it's, you know. So if we use that theorem, though, to do the Fourier integral, we break it down into two pieces. We have the uv and then the v du. The uv is this piece right here, and it's integrated from minus to plus infinity, and that whole term just goes away because of the fact that we're assuming that we have an energy type signal for x of t. So at plus or minus infinity, we're not expecting that signal to have any amplitude. So that whole integral goes away. And then we're left with j2 pi f times this other integral, which is exactly the Fourier transform. Now if that seems too hard to get a grip on, I put a second proof in here. This relies on Leibniz rule for differentiation of integrals, which I don't know if you've ever seen that before. Did you ever see that in calculus? Okay. When I've taught probability theory, I use this formula because it comes in handy in that class when you have to take a CDF and make it into a PDF. Those of you that have had probability theory know what I'm talking about. So you can look at that proof if you want to. I'm pretty sure if you were to type Leibniz rule for differentiation of integrals into Google, you'd get a Wikipedia answer for it, probably. This gets a little bit more in a more friendly format, and you can repeat it over and over again, and you will eventually get the nth derivative form. But we're just interested in applying it now that we know what it is, the j2 pi f. And this actually has another nice memory aid, which, let's see, how can I explain that? When you differentiate a signal, if you have a signal that goes through a differentiation operation, what does differentiation tend to do to a function? Does it make it smoother or spikier? I heard both. Okay, how many say it gets spikier as opposed to smoother when you differentiate? Okay, that's right. Integration smooths things out because it averages things. So if a waveform gets spikier, let's say from being differentiated, has sharper edges on it, has more spikes in it, what do you think the spectrum is going to do at high frequencies? Increase. And that's exactly what this theorem is saying. It's saying the undifferentiated signal spectrum is x of f, but when you've differentiated it, this f in here is now getting bigger and bigger as f frequency goes up, which is saying it's accentuating the high frequency components in the signal. And that leads to something else that maybe you've heard people say in electronics. What's that? Pardon me? It's an RC high-pass filter, right? So what does a high-pass filter do? It approximates a differentiator, and it accentuates the high frequencies and cuts down the low frequencies. So there's a relationship, approximate relationship between there. So sometimes people say, put this RC circuit in there to approximate the differentiation. And if you do that with a square wave, you'll see spiky peaks. Maybe you do that in electronics lab, I don't know. Have you done that? Seen that? Okay. These are classics, I guess I'd say, for electrical engineers. You know, intuitive things that you're supposed to kind of stow away in your brain for future reference. Okay, how can we use this to develop the Fourier transform of a triangle pulse? The idea here is to simply say, let's not try to Fourier transform this directly. We could do it, but what's ugly about having to do this Fourier transform without me writing anything down?
There's two parts to it.
There's two parts to it, because this is what you have to integrate. There's two parts to it, but what's particularly wrong with it in my mind is you're going to have this function times e to the minus j 2 pi ft, and you're going to have t times an exponential, so you're going to have this type of deal. And what type of integration do you have to do to get that solved? Integration by parts. Do you enjoy that? I'm not a super fan of it. As a matter of fact, if I was really having to do it, probably what I'd do is, in the book here, I'd go to the integral tables that are in the back here of indefinite integrals, which maybe isn't in this book. Yeah, it is. It is in here. It's on the top of page. No, it isn't. Where is that? Yeah, it's the fourth integral down on page 723. X to the m, e to the ax dx is in there. So I guess the fact that we had to use integration by parts to prove the differentiation theorem is some sort of conservation of integration formulas. But now that we've got that formula, now we can use it to get the Fourier transform of the triangle. So a couple options on getting this Fourier transform. One is to take one derivative. So you take one derivative and you get the two rectangular pulses that I'm showing down here. You could stop right there and take the Fourier transform of this waveform, because it's two pulses, a negative pulse, or I mean a positive pulse and then a negative pulse, and that would be two sinc functions. And then you could manipulate that. But you could also take it down even further. So option 2 would be to take two derivatives, and then you're just going to get impulses, because where this thing jumps, that gives you a spike up of 1 over tau. Where this thing jumps down by twice that, you get a negative spike of minus 2 over tau. And then when it flies back up again, you get another 1 over tau spike. Remember, this is what I was calling the operational math last time, where you're just using operational properties of the delta to say that when you have a jump, you replace it by delta. So now that we have three deltas, you can go ahead and say that, okay, the Fourier transform of the triangle from the differentiation theorem is going to be, if I take two derivatives of something, just call this y of t, and that will be j2 pi f squared times y of f. But suppose this is x of t right in here, then that would say that x of f is y of f over j2 pi f squared. It's a little bit of a substitution business, but we wanted to use this as a means to make it easier to get the Fourier transform. So we're getting the Fourier transform of x of t, in effect, the double differentiated signal, and we'll get that Fourier transform worked out as x of f, and then that's going to be related back to the Fourier transform of what we're interested in by dividing by the 1 over j, or the j2 pi f squared. It's an algebra thing, but again, I know I can prove without doing the math that it's got to be right, because when you differentiate something, you accentuate the high frequency, so the f is in the numerator. When you integrate something, you divide by the f. And we want to find the Fourier transform of a signal that hasn't been differentiated. So we're finding the Fourier transform of the signal that's been differentiated twice. So to undo that differentiation, we have to divide through by the f in the denominator, the j2 pi f. Does that make sense? So we're smoothing things as opposed to sharpening things.
So you did a substitution of x of t equals d squared over dt y t. Is that what xt equals, or is that?
This would be x of f over here. Oops. I can't draw across the page, so that's why it's complaining at me.
Okay. So
Then how do you get that over?
So I just said, yeah, actually I wrote this down wrong.
Okay.
This should be the x. But I wrote up here, just confirmed what I needed to write. This would be y of f is x of f. The hand was quicker than the brain, rather than the eye as in the magic trick. So I faked myself out. So taking the Fourier transform of the three delta functions is just simply using the frequency translation theorem, or not frequency translation, but the time delay theorem. So you take the Fourier transform of a single delta, and you just get, from the shifting property, the delta function, you get back whatever that amplitude is. Like in the center term here, it's just minus 2 over tau, and then this delta function hits right at t is equal to 0, so that shifts out 1. Or thinking of the delay theorem, it's just going to shift out the e to the minus j 2 pi f t naught, whatever the delay happens to be. So it's tau or minus tau. So you get those three terms, and then you play a game with Euler's inverse identities to build that back up as a cosine. And I look at it and I say, I know it's going to be a cosine because I have, there's the positive exponential and there's the plus the negative exponential, and that tells me it's a cosine, right? So I just need to put a 2j, just need to put a 2 in the denominator and a 2 in the numerator to balance each other out, and then build the cosine. So that's where the 2 cosine comes from. And then the center term is the constant, so that's just the 2. And then that's still not very beautiful looking, so you work harder and you say, what else can I do? Well, it looks like I have the trig identity for sine squared. And this may not be sitting right in the forefront of your brain, but it may, I don't know. Again, you have that in the appendix of the book, though. When all is said and done, though, you have something that is memorable, and that is that the triangle transforms to tau sinc squared of f tau. So it's the difference between sinc and sinc squared, between the rectangle and the triangle. But the triangle, remember, is a slightly different duration. The triangle goes from minus tau to plus tau, whereas the rectangle goes from minus tau over 2 to plus tau over 2, and it transforms to tau sinc f tau. So there's room for error, unfortunately. It's pretty nice. I mean, we're going to see why this comes into being right now when we go through the convolution theorem, because that's the example I'm going to take. Convolving two rectangles produces a triangle, and it turns out that's the motivation behind the definition of the triangle, because it's related to the convolution of two rectangles of equal width. Any questions? There are a number of things that keep swirling around, though I'm sort of moving just through the Fourier theory, but we're swirling around with different ideas. Okay, convolution needs to just be quickly reviewed to talk about the convolution theorem. Convolution is a mathematical operation in its purest form, but convolution gets introduced early in signals and systems because when you have a linear time invariant system, and we're not talking about any systems yet, we haven't gotten to that part of the review, it ends up being that the output of a system is the convolution of the input with the system's impulse response. But if we're void of linear time invariant systems, which we are right now in our discussion formally, just the definition of the convolution is this integral. And I guess, what was I doing? When I was working on the book, I thought it would be cute to put in some definitions from the dictionary, and my editor threw them out. They said, we don't do that. But I thought it was cool. You look up convolution in the dictionary, and it says to intertwine something with another something. And all of you have done convolutions before, and I think you'd agree it is an intertwining, and it's kind of a nightmare when you first start doing it, because it's like, this is not a fun thing. And then convoluted comes from convolution, or one comes from the other. And if something is really hard to understand, like Fourier theory, you say it's convoluted, right? Because it's difficult to understand. So these are the two forms of the convolution integral. One special case of convolution, though, that you never want to turn down if that's your choice, I mean, if you have to do a convolution and you said, can you give me one with a delta function in it, I'll gladly do that one. So that's this result right here. Because of the sifting property, the delta function, when you push these two signals into the convolution integral, the delta function runs the show. The delta function sits in here in the integrand, and it says, I'm only going to be active when the independent variable, or the variable of integration lambda, happens to hit t naught and make that argument go to 0. So when the delta function turns on, when lambda sweeps through t naught, it just simply replaces lambda over here with t naught, and that's what sifts out then. So you get x of t minus t naught. Is that good? So this is one you don't want to circumvent if you had your choice.
Question. Does order matter in convolution? I can't remember.
It doesn't. It doesn't. So it's commutative. And that's, you can prove by change of variables in the formula. Then you have to go through your limits and the d lambda and all that kind of stuff, but you would do something like t minus lambda equals sigma up here, and then d minus d lambda is equal to d sigma, and then you do your limits, and then you'd have a flipping of the limits because of the minus d lambda and d sigma, you know, all that stuff from calculus, but it would, then you would get this answer down here if you did that. I'm willing to bet you did that in 3205 maybe, I don't know. One of those classes. In 2610, it's only the discrete time version, which is the convolution sum. At least that's what I covered. So rectangular pulse convolution, just a quick review on this, because there are some homework problems on this. This is the standard classical convolution problem to work. So you've got two rectangles, identical durations. One's going to get convolved with the other. So one of the things you have to remember about doing convolutions is setting up the functions that comprise the integrand. So in this case, the way I've got this set up, I'm doing the convolution where I've got x1 of lambda times x2 of t minus lambda d lambda. So I sketch what's in the integrand. I've got x1 of lambda here, and then I've drawn x2 of t minus lambda pushed off to the left. But that's purely a matter of what I choose for t with respect to being on the lambda axes. So the first thing that you have to remember is how do you flip and slide a signal. So flipping a signal just spins it right around where the axis, time axis or lambda axis equals 0, and then when you put in a second argument, you actually are able to slide it back and forth. There's different ways of getting at this, but probably a favorite of mine would be to say, I would look at t minus lambda is the argument in here, and the pulse function is active when its argument sits between minus tau over 2 and plus tau over 2, right? That's the definition. That's where the rectangle is active. So then you can work with that. You can say, I know that the argument of this function x2 is going to be high or active when I'm between minus tau over 2 and plus tau over 2. So then you can just solve out for that on the lambda axis. So you'd solve out for, in terms of lambda, you'd say lambda has to be less than or equal to, so if I put these two sides together, lambda has to be less than or equal to what? Moving the lambda to the left. Less than or equal to t plus tau over 2. Is that right? Did I do the algebra right? And that's this limit right down here. And then if I did the opposite case, I would sit on that side and say lambda has to be greater than or equal to, just moving it to the right-hand side, greater than or equal to t minus tau over 2. And that establishes that. But there's a lot of other ways of doing this. I'm just trying to sort of get your memory going on how this sets up. Another way of thinking of it is the signal is centered on t if it was centered on 0 to begin with. So that tells you that the center is right in here. So now that you have the time reversed and shifted signal on the lambda axis, it's just a matter of looking at the cases as you consider different values of t in the convolution integral. The first thing that you want to remember, though, about doing convolutions is the output of a convolution starts at the sum of the two starting values and ends at the sum of the two ending values. That's just a property, and I won't take the time to prove that right now. But in this case, both pulses start at minus tau over 2 and end at tau over 2. So based on the rule I just spoke, the convolution is going to begin when at minus tau over 2 plus minus tau over 2, the two starting points. Okay? And that's true right here. In particular, that's true here, because if I get my eraser to work, this guy is going to be equal to that when what? T is equal to tau. Or t is equal to minus tau. So that's where the first overlap occurs, when t is equal to minus tau. And then the end of the active region for the convolution is at the sum of the two ending values, which would be tau over 2 plus tau over 2, or tau. So it starts at the sum of the two starting points and ends at the sum of the two ending points. And that holds whether or not one or both of the signals is going to infinity. You know, if one of the signals ends at infinity and the other one ends at, say, 1, it's 1 plus infinity, so it goes to infinity. They are helpful. They're kind of like a dummies check. I mean, as in a real dummy, as opposed to the For Dummies book that I've been working on, where I did include that. But you can diagram that out and prove it. So there's 4 cases to consider. One is when there's no overlap, so t is less than tau, that's 0. And then when t is between minus tau and 0, you've got what I call the partial overlap, and that's shown down here in this bottom figure, where you're partially overlapped, and then you have to set up your integral, and your limits on your integral are going to be controlled by those two numbers, because that's where the overlap of the integrand functions occurs. And what I mean by integrand functions, it's all about setting up this integral where those two functions mesh together and they define an interval to integrate over. So you integrate from minus tau over 2 to t plus tau over 2. And you're integrating a constant, because you don't see anything inside of here. You've got 1 times 1 in that interval. So that just becomes lambda. Plug in the limits and you get tau plus t. Second case is when you've crossed over the middle. In other words, you've gone past the full overlap case, and now the leading edge of the pulse that's moving, this guy right here, is greater than tau over 2. So you've just got, again, a partial overlap. But it's the opposite scenario. Instead of what I call the leading edge, where it's just starting to overlap, now it's slid by and it's now the trailing. The trailing edge has got the overlap. And again, now the limits are set by those two guys.
So, sorry, question.
Okay.
When you were solving earlier for lambda is greater than or equal to t minus tau to the t,
Whatever I had in the previous page.
It was up there. Does that factor into your integral at all? Is that your integral limit?
Yeah.
Depending upon it? Is that
It factors in because it's what, just getting kind of cluttery here. It's what allowed, it's what set those values.
okay? So that's
And that's like my pulse has got these edges on it. And if you're thinking in terms of digital waveforms in this case, but just a waveform in general that's sliding along, I call this the leading edge, and that's the trailing edge. Is that a good way of looking at it? Does anybody get on board with that idea? So the leading edge first engages the fixed pulse, x1, and that's the picture we had here. And then when it slides far enough over, the leading edge has already gone past the end of the fixed pulse, and now it's just the trailing edge that's interacting with the fixed pulse. And that's this scenario over here. What don't I like about convolution? It's so blasted tedious. I mean, I guess I'm not sure which is worse, convolution or doing a Fourier transform of a waveform that's kind of weird. But does anybody have an opinion? Worse? Remember I told you that the chapters in my book, these were the two most difficult chapters to edit, and they made me redraw almost all my convolution figures because they just wanted more clarity, more spread, and they didn't want to have it be simple. And I can't use colors either because it's a black and white printed book. So here the colors I think help. But rectangles are pretty benign. It's like, is that the real world? Well, it's a starting point to have two rectangles. So finally, when you get to case 4, you've got no overlap and you're done. So you collect the results together and you have a 4-part solution. Piecewise continuous is what it's called. And then you can cluster things up. So you can take these two pieces that sit in here and say that, oh, that's just, get the absolute value sign included in there. Absolute value signs are nice to look at, but when you actually have to do math with them, they're actually a pain. And if you're writing code, they're also a pain. If you're trying to describe something mathematically, they can be kind of a pain. You generally have to unravel the absolute value sign, even when you're programming something. But this is the definition of the triangle pulse. The only thing that's missing is when the two waveforms are perfectly overlapped, and this is another property of convolution. So you've got a rectangle here, and then we have the blue rectangle that slid across. And when it was perfectly overlapped, which was when t is equal to 0, these are perfectly overlapped with each other. So we have 1 times 1 all the way across, and then it's the full width, and that is tau. So at the maximum overlap, you get the product of the two waveforms integrated. In this case, it's a constant, so it's 1 integrated from minus tau over 2 to plus tau over 2, which is just going to be tau. So this triangle pulse over here goes up to tau, starts at minus tau, ends at plus tau. It has an amplitude of tau. So when you want to explain what the final result is, rectangle convolved with rectangle, it's the triangle, but you have to include the fact that the amplitude is now tau. And that has to do with the area property of the convolution. This is only a small piece, unfortunately. I mean, I'm not going to keep going on this, but there's other examples of convolution. Like a rectangle with a different size rectangle gives you what? Trapezoid, right? And then the peak is, well, to get that peak, it's again the overlap region integrated. That's the maximum it goes up to, but it holds that peak for a while because as it's sliding through, like you've got a long thing and a tiny thing In the middle, it will first do that, and then it will hang out inside of here for a while. Then finally it slips by. So that lets you get the trapezoid shape. The convolution theorem makes things pretty nice if you can get to the frequency domain to take advantage of it. Convolution theorem, since I spent quite a bit of time on that, just says convolution in the time domain is multiplication in the frequency domain. So to see if the sinc and the rectangles and all that stuff work out, let's just go back and revisit the rectangle convolved with the identical rectangle and see what happens. We know it's a triangle multiplied times tau, so now we go and apply the convolution theorem, and it says in the frequency domain it should be the Fourier transform of the rectangle times the Fourier transform of the rectangle, which should be tau sinc f tau. Remember, this is the memory thing I was talking about a while ago. Tau sinc f tau for a rectangle. Then the whole thing squared, because the spectra are identical. And because we've already looked at the Fourier transform of a triangle, we factor out one of those taus, and then we have tau sinc squared left inside the parentheses. And remember that tau sinc squared is the Fourier transform of a triangle. So it does work out. So it just formally reestablishes what was established earlier. Now, a dual of the convolution theorem is the multiplication theorem. And you're probably thinking, this one can't be all that important. Well, it turns out it is, to a certain extent, because of the fact that we multiply signals together. Usually it's a cosine that we multiply times another signal, but it's still useful to know that when you multiply signals in the time domain, you convolve them in the frequency domain. But remember, convolution with delta functions is not too bad, so that's kind of what we'll be taking advantage of. And I'm not going to really demonstrate that right now, but if you have to do a convolution with a delta function and it happens to be in the frequency domain, it's not that bad of a deal. Before I can actually do that, though, I have to establish how it is we can get delta functions in the frequency domain, because right now they don't legally exist by the definition of the Fourier transform. We have to bend the rules slightly and establish what's called Fourier transform in the limit. Remember, tracing back to 2 weeks ago, periodic power signals have a line spectra, and we use the Fourier series to get that spectrum. That was the way that we get the frequency domain representation for a periodic signal. We go to the Fourier series as the tool of choice. Aperiodic signals, they have a continuous spectrum, and that's the Fourier transform. A wish or a desire, and I think this is a good student wish too, is to say, wouldn't it be nice to have a unifying approach to spectral analysis so we could actually bring everything under one roof, so to speak, and not have to worry about, is this a Fourier series or is this a Fourier transform, and how do I handle it? So that's what we're going to do with the Fourier transform and the limit idea. The bottom line is we get there by allowing impulses in the frequency domain. And that's what the Fourier transform and the limit approach is. Now, I'm not sure how this is treated in 3205. I honestly don't know because I haven't studied the book. Is Fourier transform and the limit something you remember from that book? But yet you've probably seen something like the Fourier transform of a constant A. What would that be from 3205? Probably with your omega domain it was 2 pi times delta of omega, right? But how did you come to believe that to be the case? From the duality theorem, or? Okay. You probably started over here and then went in that direction, would be my guess. Because otherwise, this signal that's a constant just is not something that obeys the requirements for being Fourier transformable. So that's the example I'm going to take here. Normally, to be Fourier transformable, one of these conditions have to exist, and one of them that we were looking at, that's looked at earlier in the notes, is that has to be true. And a constant definitely violates that. But a Fourier transform in the limit kind of, like I said, bends the rules. So the Fourier transform in the limit idea says, let's write the constant as a rectangular pulse signal right here, and then we'll let the width of that pulse go to infinity. So we'll look at it as being a finite duration pulse. We'll Fourier transform that pulse, and then after we Fourier transform it, we'll let t go to infinity. So it's interchanging orders of operations, which engineers are notorious for doing, because engineers just say, I'm going to do it because I don't know what else to do. Whereas mathematicians would say, oh, I got to be very, very careful if I'm going to interchange the order of one operation and another when a limit's involved, because I might get the wrong answer, and that would be devastating. And for an engineer, I mean, we should think devastating, because health and safety is at stake in what we design. But this is not a new thing, so you have to believe me when I say, well, do it carefully, and it does work. So you take the Fourier transform of the rectangle, and you get tau sinc f, or t sinc ft, and I just have a picture drawn here of what it looks like for two different values of t. It's a sinc function, and then as t gets bigger, the sinc function is getting more and more compressed on the time frequency axis. And if you were to keep doing that, it would just compress down to this spike that would have little wiggles on it, but they wouldn't even be discernible unless you were to zoom in really close to it. If you just stay at the same zoom level and increase t, it's going to compress down. And kind of the moral to the story is, you look at this and say, that makes sense intuitively, because as the signal goes out for a really long time, as t gets big, it looks like a constant. There's no variation in it. The spectrum is compressing down to just one spot, namely f is equal to 0. And that makes sense, right? A constant signal should only have spectral content at dc, because there's no variation in it. So that's kind of that's the birth of the Fourier transform in the limit idea. It makes sense intuitively. If we also go ahead and try to integrate the sinc function, you'll find out it has the t sinc ft has unit area, and that's one of the requirements to be a approximated delta function, some test function that you can make compress down to be active only at a point. It has to have a constant area, and this also does.
So to evaluate that limit for the sinc function, if you're doing it for a constant, you would have to use L'Hopital's rule then to evaluate that limit such that...
No. The reason why is because I just take this picture right here and I keep going on this, and eventually I'm saying that it's looking like it's behaving like a delta of f, simply because as t gets very, very large, the spectrum looks like it's non-zero only at a point, and its area is equal to unity. And those were the properties of the delta function, right? It's a little bit hand-wavy, though, just the same. But it is the idea of the Fourier transform in the limit. The mathematicians down the hallway from me would not be as fond of this as an engineer would be. I mean, we can kind of get away with this for another reason, too, and that is there any signal that really starts at minus infinity and goes to plus infinity? Not really. So that's kind of an extra little safety valve there, I guess, to know that we really don't have that happening. So that's the exciting Fourier transform in the frequency domain f. Constant becomes a delta of f. So it puts all the punch of that constant or dc right at zero frequency. And intuitively that makes, excellent sense. Question?
Yeah, is that an integral right there? Is that the inverse Fourier transform? Or what is...
This integral? Yeah. That's just integrating the sinc function to see if its area is equal to 1. Just testing it. Remember we had the delta function, test function earlier that was something that was 1 over 2 epsilon.
Yeah.
This was called delta epsilon of t.
Yeah.
We wanted to integrate through that and see does that area equal 1, and that does, right? And then we want to see if the limit as epsilon goes to 0, is it behaving like a delta function? And that's the same idea. The sinc function is another test function for a delta function. And also if you take the inverse Fourier transform, and this is what I was thinking you might have done in 3205, the inverse Fourier transform of a delta of f just sifts out that value and you get a, just like that. It's just like, this is a no-brainer. Why didn't I think of that? The problem, though, is when you start to go in the other direction, that's where you violate the definition of finite energy on the signal. So you have to be careful when you deal with Fourier transforms in the limit, but in this class they are extremely valuable. It's a limiting idea, but it provides all the right sort of information, and it works with the theorems and things. So there's a few more theorems. If you just have a complex sinusoid times a, that from the frequency translation theorem, that just shifts the spectrum up to f naught. If you go with a cosine and just Fourier transform that, and this is like unheard of, this is a periodic signal, we can now Fourier transform it. We get two delta functions. We get one at f naught and one at minus f naught, and then we get a complex phase. That's the line spectra, or like the line spectra. Rather than having the formal line spectra interpretation from the Fourier series, now we have the Fourier transform, which is placing things down with the delta function. Now the line spectra idea just said we have to place spectral lines down based on the Fourier coefficient, magnitude, and phase, and whatever harmonic we're at. Whereas now with the Fourier transform, it's kind of been automated for us because the delta function in the frequency domain just automatically locates that spectral line. Do you find that acceptable, or does that sound confusing? I kind of like it myself because it's like I don't have to worry about thinking x of n. Where do I put that? Well, I have to know, okay, n is the fifth harmonic. What's the fundamental? It's 10 kilohertz. Okay, so it's at 50 kilohertz. And then I've got one at minus 50 kilohertz for x of minus n when n is equal to minus 5 or whatever. Whereas the delta functions just sort of manage themselves. Okay, so we have one little property here that I'll just make quick mention of, this thing called the reciprocal spreading property. And this is extreme exaggeration that you can't really build, but it is, there's middle ground on this too. And this is from the duality theorem, or just Fourier transform pairs that we've developed. A delta of t, just a single spike on the time axis, is a spectrum that spreads over all frequencies. So a short blip in time is a super wide spectrum, and then the dual of that is a signal that's constant forever, is just a spike in frequency. And then the middle ground on that is, things that are rather short pulses have rather long or broad spectra. Things that have rather slow-moving long pulses tend to have a very rather narrow spectrum. The idea of reciprocal spreading is saying what I see in the frequency axis is the inverse of what I see on the time axis. Like the spectral width is about 1 over the pulse duration, that type of thing. Or it's proportional to that in some way. Okay, Fourier transform a periodic signal, and then I'm going to look at some homework and decide where the quiz is going to be on.
We are going to have a quiz then, I believe?
Yeah, yeah. I decided practice is better than no practice. It'll make you better for the exam. And then if I have enough of them, I'll drop 2 of them maybe. Okay, Fourier transform a periodic signal. This is now trying to unify Fourier transform theory and Fourier series ideas. If we have a periodic signal, we can represent x of t using Fourier coefficients and complex sinusoids. So now we go ahead and Fourier transform both sides. So we Fourier transform that x of t to get x of f. Then we go over here and Fourier transform that term by term. But the term by term Fourier transform from linearity is just Fourier transforming the complex sinusoid, which is just a delta function shifted to the frequency n f naught. So our spectrum is exactly a line type spectra, only with the lines located by the delta functions automatically. And the x of n's are the Fourier coefficients from before. They have magnitude and phase. So, like I was saying, it's just the line spectra gets placed automatically by the delta functions. Now, the negative of this is that you have to have the Fourier coefficients already in order to make this work. So, we do have a theorem, though, that's going to manage to even circumvent that. And for those of you in the lab, it's kind of a handy result. It's a couple pages away, though. So I have this little picture to say, what's the difference between a line spectra and a continuous spectrum? Well, one is the sum of phasors. That's what the Fourier series formula gives you. And when you have a continuous spectra where you're using delta functions for periodic signals, you end up integrating those impulses, and those come back to be phasors when you do your inverse Fourier transform. So there's no difference. They're the same.
Because integrating the impulses is just a shifting property.
Well, yeah, the sifting property. Yeah, exactly. In other words, if I go to inverse Fourier transform this guy here, I will sift it back to the Fourier integral to that. I'm going to have to show you the fancy theorem next time. I'll probably have that on the exam at some point, though. This neat little theorem. If you want to go take a look at it, it's not going to be on the quiz, but the theorem I'm speaking of is this thing right here, direct approach for the Fourier transform of a periodic signal. You can get effectively the Fourier coefficients just by Fourier transforming one period of the waveform. That's what it boils down to. This is hidden away in the book, and to me, when I first learned about this a long, long time ago, I thought this is one of the greatest things there is for Fourier theory. It's like I can do away with Fourier series forever. I can just work with the Fourier transform and just stick with that. I mean, not quite in the limit like that, but it's kind of nice. My editors didn't like it a whole lot. They thought it was way too hard, so I'm interested to see what you guys think of it. So let's look at some homework. There's some properties that we didn't really talk about yet, but this homework problem right here was just Fourier transforming 2 rectangles. Pretty easily done, right? What does it take to do this Fourier transform?
Oh,
No, you didn't have to.
Yeah, I don't
You
think
just
you had
said
to
if
do
it was
it.
odd or even and if it was real or imaginary.
Okay.
Is all you had to do for that one.
Yeah, okay. Well, suppose you wanted to take the Fourier transform of this. I'm getting ahead of myself then. How could you Fourier transform this? The Fourier transform of a rectangle is a sinc, right? And then you have to use what theorem? What property or what theorem? Linearity is kind of automatic, but the time shifting theorem, right?
Oh, okay.
okay. Yeah.
So it'd just be a time shifting operation. And because there's nothing, oops, it's like there's a 1 sitting down in here, right? So this is going to be sinc f tau, and then because it's shifted to the left, it's going to be an e to the plus j 2 pi f times that time factor, which is 1/2, and then the second term is going to be the same sinc f tau, or f. I got this wrong. Should just be f, right? But it's going to have the opposite shift factor, so it's going to be e to the minus j 2 pi f times 1/2.
Looks like a sine.
Yeah, this is that a cosine or a sine? Sine, right? You could pull that back up into a sine. Then you'd have a 2j that would pop out of there, and that's why I say down here it's purely imaginary because a j pops out of there. But you're right, in this problem you didn't have to go that far.
I have a question on that. How do you know that? Well, I guess it's because it's a sign. That's how you know it's not function with that. Well,
Yeah,
I was wondering-
the sign makes it odd. Well, this is an odd function to begin with, right?
Right. So, does it follow then that if a function is odd in the time domain, it's odd in the frequency domain? Like, how do we know that without actually?
Now, a real signal always has, no matter whether it's even or odd or whatever, a real signal always has a Fourier transform, and this is in one of the properties somewhere in the notes. Fourier transform is always, magnitude is always an even function of frequency, and the phase is an odd function of frequency. That's always the case. Even or oddness on the time axis just relates to whether or not the Fourier transform itself will be purely real or purely imaginary.
Because one of the things it asks is whether the Fourier transform of the signals will be even, odd, and either. And I didn't know how to do that without actually taking the.
I don't think they meant that, though.
They were
Oh.
just saying if the time signal.
If, given the signals below are real, let's see, let me just read what it says.
Yeah, actually,
Yeah, whether the Fourier transforms are real, imaginary, or neither, and whether they're even, odd, or neither. So, Dr. Ziemer is like any textbook author. He's famous for asking questions that are trying to see if you're paying attention or not. So, the Fourier transform is either going to be real, it's going to be real, imaginary, or fully complex, but the magnitude of it will always be even, the phase of it will always be odd. So when he says even, odd, or neither, I guess he's looking at if you're looking at the complex quantity for a complex valued Fourier transform, it could appear as an even function or as an odd function. So I guess the statement is valid. In this case, it's going to be odd for this example because this works out to be 2j times the sine of pi f.
So I shouldn't be worried that I don't know how to figure out whether it's odd or even in the Fourier domain without taking the Fourier transform of it. Because it's clear to me that the imaginary part is completely odd, but that's only because I took the Fourier transform. But it says without even taking the Fourier transform of it, tell me if it's odd or even.
Yeah, maybe there's some fallacy in this. I don't know.
Yeah, so are all odd functions, are they just imaginary?
Their Fourier transforms are imaginary, yeah, purely imaginary, and that's why there's this 2j out in front of that. Okay, what's on the next problem? This one is a little convolution problem. It's a little house problem with a convolution. So if you had to do something with rectangles and convolutions, what could you do? If you didn't have the convolution theorem, you'd just have to convolve it brute force. But because convolution is also distributive, you can convolve it piece by piece and then put it back together again. So in this case, you've got a rectangle. I mean, 2 pulses of equal widths gives you a small trapezoid, which is the picture here for the 2b. And then The other one is a triangle. So you have a triangle stacked on top of a trapezoid, and it gives this goofy kind of shape. Because you've got this, and then the other one is like that.
They're multiplied together?
They're added together.
Added together. Oh, yeah, that's right.
Computer just stuttered on me. We're way out of time, though. They're not busting the door down on me.
Oh, yeah.
I think what I'm going to feel safe in doing is these next two problems.
Okay.
But definitely, you know, all the nitty-gritty details of some of these convolutions, you'd never see that on an exam or a quiz. I mean, this problem right here is just phenomenally tedious.
The last problem.
I think it's
Yeah.
38.
Yeah.
Or is that 5? Was that 4 or 5 that you said the students?
It's the fourth problem, 235C, I guess. I don't even know what we have in the next one.
Yeah, if you're doing exponentially.
What is the next one?
That's the next one.
This one's a little bit tedious also, but this one is gated by a rectangle, so you can use the multiplication theorem here if you want to. There's different ways of getting at this, though. There's always a couple of different ways.
There's always a really tough way or really easy.
Exactly.
There's a tough way.
really tough way.
This problem also gets into that theorem, which we didn't get to, so that's why I'm going to hold off on that. So just step forward, two problems, and look at those.